This is Mark Anderson for Keller Community College, and we're going to be looking at graphing logarithms in this video here, and we're going to start off by something I like to put on my tests, which is showing all the work displaying that a logarithm is the inverse of an exponential. So what we're going to do is start off with the ability or the attempt to try to graph log base 2 of x. Now, there are some graphing calculators that allow you to change the log base, and some of the TI graphing calculators cannot. It all depends on a ROM version or model number, and I'm going to teach the rest of this video as if you do not have that special or newer Texas Instruments graphing calculator that can do a different base other than log base 10. So what I'm about to do is I'm about to show you how I want this shown on this part of the test, because your job is to show that the logarithm is the inverse of an exponential. And the base of this problem is base 2, so we're going to start off by graphing y equals 2 raised to the x power. And I'm going to plot 5 points, 2 negative, 2 positive, and 1 at 0. And what that's going to give me is going to give me a very nice table that I can easily graph. So for step 2, after I write my equation, for step 2, I'm going to write my table. Again, starting with negative 2, and going to 2, there's my 5 points. So 0.25, 0.5, 1, 2, and 4. And so now I'm going to plot this on the x and y axis. Negative 2 is at 0.25, which is like a softball lying on the ground. Negative 1 is going to be 0.5. 0 is going to be 1. 1 is going to be 2. And then 2 is going to be 4. So this gives me a nice exponential growth, excuse me. And what I'm going to do is graph this logarithm by treating this like an inverse. When we take an inverse of a function, we switch the x and y. And if we literally switch the x and the y positions of this table, what we now have for our new x and y, which is going to be our logarithm right here, this is going to be 0.25 on my x, 0.5 on my x, 1, 2, and 4 all on my x. And my y is going to be negative 2, negative 1, 0, 1, and 2. So now I get to put this up on the graph. So at 0.25x, which is about a little bit, a quarter away from 0 there, we're going to drop this all the way down to negative 2. And then at the halfway mark, we're going to put at negative 1. 1 is going to be at 0. 2 on the x is going to be 1 on the y, and 4 on the x is going to be 2 on the y. And so here is our logarithm graph. So this is our graph of y equals log base 2 of x, and this is our graph of y equals 2 to the x. And so there I have now shown that a logarithm is the inverse of an exponential. And if I was to type this in on the calculator, which I will show you at the end of this front page here, or this one part of this page, I will show you how you would type this in and verify that this is in fact the log base 2 of x. Now for this next example, I'm going to do log base 4 of x. So we're going to start off by graphing y equals 4 to the x power, which in step 2 is going to be my x and y of negative 2, negative 1, 0, 1, and 2. Now, I'm actually not going to go to 2 because that is going to go way far off the screen. I only have 5 tick marks in either direction, and 4 to the second power 16. So these will do me fine. This is going to be 0.0625. This is going to be 0.25. This 0 is going to be at 1, and 1 is going to be at 4. So this is going to start off negative 2 at 0.0625 on my y. 1 is going to be at a quarter, and 0 is going to be at 1, and then 1 is going to be at 4. So this is my... Oh, shoot. Looks like I missed that dot quite a bit. Well, anyway, I'm sorry about that. Let me redraw that line just a little bit sharper. There we go. So there's my line that goes up in that direction. Now what I'm going to do is go and do the other one. So my other one is going to be the flip. This is my log equation. So I'm going to flip my x and my y. So 0.0625 and then 0.25, 1, and 4. And on the other side, negative 2, negative 1, 0, and 1. So negative 2 is at 0.0625, which is going to be over here. Negative 1 is going to be at 0.25. 1 is 0, and 4 is 1. And so here we go. Here's my beautiful curve like that. Alright, so there, my friends, is the logarithm. This is the log of base 4 of x, and this is going to be my exponential, 4 to the x. And I want to actually now, before I flip to the next page, is I want to compare domains and ranges. So if I look back at this exponential, so we're going to look back at the domain and range of this function. So what we have here is a domain that is all real numbers, because this goes infinitely to negative infinity in the x direction and positive infinity in the positive x direction. The range is going to be where y has to be greater than 0, because this exponential growth line will never actually get to 0, as explained in a previous video. Now down here, if we look at the domain and range of this function, what you'll see is that the domain is that this line will never be crossing the y-axis. So in this case, x is going to be greater than 0. And in this case, the range is real because it goes infinitely to negative on the x in the y direction, and infinitely in the positive y direction. So you can see that the difference between the domains and ranges are flipped just because of their inverse property of each other. So we flip the x and y, which literally flip their tables, and it literally flips their domain and range as well. You'll note that we do have to talk about x in this domain and y in this domain, and that's just because of the rules of set notation. Alright, so one thing I want to do now is I want to bring up the graphing calculator before we move on to the second page here. I want to bring up this graphing calculator, and I want to show you that there's a way that we can use the change of base formula to graph this function. Now you have written down on your paper the table for that log, so what I'm about to do is use the change of base formula by saying that our numerator of the change of base formula is going to be log base 10 of x, and our denominator is going to be log base 10 of 2. And I would never say log base 10, but I'm trying to remind you that this is a common log which has a base 10. Now let's go to our graph. And you'll see this kind of matches the hook that we created down here for this picture, which is now gone due to the fact I'm using the calculator. And if we look at our table, you'll see that there's an error up to and including 0 because our domain, our x, yeah, you're right, I was saying it right, our x could not be 0 or less. So you'll note that we have 1 is 0, 2 is 1, 4 is 2, and 8 is 3. So you'll see that these are the points that we had on our graph for our logarithm. Now some of the decimals of course aren't here, but these are the whole numbers that I can choose to graph. Now what we're going to do is we're going to go to the next section and we're going to graph 5 logarithms using our technology. We're also then going to state the domain and range of each function. Now this first picture right here, I'm going to have to kind of keep it near the top, that way we can kind of get all the stuff in there. And what I'm going to do is show you the way to type this in, and then I'm going to kind of show you on paper how to get it into the calculator. So in this case, this is log base 2 x plus 2. So our numerator is log of x, our denominator is log of 2, and then I'm going to add 2 to that, and this should give us our table that we need. Now what I want to do is I want to go to the first error, which kind of gives us our asymptote line, or our point of no return, and I'm going to graph the point 1, 2, 2, 3, 4, 4, and I'm also going to go to 8, 5. I'm going to get a couple of easy to plot points, so let us go and graph this. Okay, so what we have here is we have 1, 2, 2, 3, 4, 4, and 8, 5. Now one thing to note is that our 0 in this table was an error, and so that kind of creates this asymptote line, this line that I cannot cross when I create my logarithm graph. And just as a reminder, the way that I typed this into the calculator, which was log of x divided by log of 2 plus 2. This plus 2 is going to shift the graph vertically up 2 units. That's not going to actually affect our range, our y values, because shifting something up and down doesn't change the y, and you'll see that as we type it in. So 0 is an error on the x, so there's our asymptote line. 1 is 2, and 2 is 3, and 4 is 4, and 8 is 5. So we're going to connect these in a nice swoop, but I also need to connect my tail at the bottom, and that tail is going to go to the 0 but never ever touch 0 on the y-axis. So that means my domain is set up where x cannot be negative or touch 0, so x, whoops, excuse me, I wrote this the wrong way, x has to be greater than 0. And our range is all real numbers. So that +2 in the problem shifted the graph vertically 2 units up, but that doesn't affect the range, which is all real numbers. It also doesn't affect the domain, which again stayed at that dotted line. Now the next example we're going to do is going to affect the range, or excuse me, the domain, because what we're going to do is we're going to have the x plus 2 in the numerator. So here I'm going to have log of x plus 2. Delete everything else there. And that's going to be in the top of my change of base formula, divided by log of 2. Now, on newer calculators, in the math button, you can actually go and find that there's something called log base. It's near the bottom of the option menu. This calculator doesn't have that, but some of your newer calculators does, and you can just put the 2 there for the base. But this is really nice because you can use your change of base formula. You can look at the table, and you'll notice that the table starts with an error at -2. So we're going to graph that -2 as an error. We're going to graph -1 at 0, 0 and 1, 2 and 2, and 6 and 3. As you see, if I scroll down, 6 and 3. Again, let's go back to the y equals, and I will move the picture down just a little bit here. Whoops, I gotta get the graph centered. Okay, calculator back, and here we go, and freeze. Let's get that table, the one I talked about. So our -2 was going to be an error. So that's really where our asymptote line is going to be. This is the place where our line will not cross. It'll get infinitely close to it but never touch it. -1 is 0. 0 is 1. 2 is 2. And 6 is 3. That's a good shift on that graph. So we're going to plot these points here. So -1 is 0. 0 is 1. 2 is 2. And 6 is 3. So this graph with the +2 got shifted to the left 2 units. And in a previous video, like I've said before, the horizontal shifts are opposite what you think. You would think that a +2 would move it to the right, but in fact it moves it to the left. And we've seen in finding zeros of parabolas, and also now in this shift, since we've had exponential shifts in 2 units earlier, these horizontal shifts are opposite what you think. Okay, domain and range. Our domain is now going to be a little bit to the left, so x has to be greater than -2, but it will never touch -2 on that line. And the range is going to be real, because this goes infinitely down to -infinity on the y and +infinity on positive y. So it looks like our domain and range is going to be affected if we have a shift inside of the equation itself, but otherwise the domain is going to be x is greater than 0 and our range is going to be all real numbers. So let's take a look at the next equation. Now the next equation is going to change by putting a 2 in front of the 2. Then we're going to type in log, and we're going to use our change of base formula to have log of x divided by log of 2. So here's log of x divided by log of 2. Alright, let's go take a look at the table. First of all, we have our 0 is our error, so that's going to be where our asymptote line is. And we're going to graph the points 1, 0, 2, 2, 4, 4, and let's get another good one. Oh, 8, 6. Alright, so going back to the graph, let's take a look at that. And I'm going to freeze this and make my table based on this 2 log of base 2 x. So here's the table. The one I said I was going to do, our 0 is the error. And what we have now is we're going to have 1 is 0. We're going to have 2 and 2, 4 and 4, and 8 and 6. So what this is doing by putting a 2 there, it's doubling all of these possibilities. So instead of 0, 1, 2, 3, it's 0, 2, 4, 6. So if you compare that to the 1, 2 above this, or just a plain old log base 2x, you could see that it's double the y values, and that's kind of what you'd expect if you just multiply all of these by 2. So we're going to have our asymptote line here at the y-axis, and then we're going to go 1, 0, 2, 2, 4, 4, and then 8, 6. So there's my hook. And then I'm going to drop this tail down below, and we're going to see that our domain is another one where x has to be greater than 0, and our range is going to be all real numbers. Okay, 2 graphs to go. Let's move down to the bottom 2 here. Here we have, and I kind of put these side by side, but I put them on different graphs because here I have half log base 2 of x, and this is double log. So what I'm going to do is actually kind of compare them on the screen here. So instead of this being 2, I'm going to put down 0.5. And let's get the rest of it into the calculator. Log x divided by log 2. Okay, so the first graph is doubling it. This graph is cutting it in half, and you can see that the y height is half as high. Actually half as high as a normal non-modified logarithm. So you can see that this one is definitely a fourth as high because it is, half smaller than just a normal base 2 logarithm that would actually split the middle here. So let's look at our table. Our table is going to start off with, I can compare the two of them. They both have 0. This one, though, I will have to settle for some decimals. So I'm only going to be talking about y2 right now. So 0, 0, 2.5, 4, 1, and I think 8 is going to be 1.5, and it is. So let's go graph this second line right here. I freeze the screen, and now I'm going to graph this 1/2 log base 2 of x. So recalling the table I mentioned, so here's my table. 0 is error, which is going to be my asymptote line going vertically. I'm going to have a 1, 0. I'm going to have a 2 and a 0.5. I'm going to have a 4 and 1, and I'm going to have an 8 and a 1.5. So let's go plot this all on the screen here. 1, 0, right there. 2.5, 2 and 0.5, 4 and 1, and 8 and 1.5. All right, so here's my hook, and then here is the tail, the domain, where x has to be greater than 0. And unless, again, if you're looking for this to ever change, that would be if I put a plus or a minus something inside of this x right there to get that to shift left or right. But instead, our range is going to be all real numbers. So for our final equation, this is going to be kind of interesting. We got negative log base 2x. So I'm going to clear both of these out because this is going to be an interesting problem. Make sure you click the negative key instead of the minus. It'll let you put a subtraction sign there, but it'll then give you an error. And then we're going to go log x, which is this part, divided by log 2. And if you're curious about why I'm using this, it's because the calculator cannot do the different base, and I'm using the change of base formula to compensate for that. So let's look at the graph. Here it is. Whoa, check it out. The hook is actually going up this way. And we can see that on the table, and I'm going to go and start with 0 for an error. So let's go and freeze that table and show you what I'm going to graph. Now I did actually copy down another this table earlier on another sheet of paper, so I do happen to have that in front of me. So 0 is error, 1 is 0, 2 is negative 1, 4 is negative 2, and if I scroll down further, 8 would be negative 3. So my 0 is error, so there's my, come on. There's my asymptote line. Alright, 1 is 0, 2 is negative 1, Oh shoot, I put my 1 at 1. I'm sorry. So forget about that dot. Okay, 1 is 0. All right. Ignore me. So 1 is 0, 2 is negative 1, 4 is at negative 2, and 8 is at negative 3. All right, so I'm going to make my hook, and then I'm going to continue drawing this up to the stratosphere, where my domain is, again, like all the rest, except for that second problem on this page, or the second of 5 examples. X has to be greater than 0, because x will never cross the dotted line, and this is going to be all real numbers. Alright, well thank you for watching all 7 examples about how to graph a logarithm. And again, if you have a graphing calculator, you should click Math right there, and this does not have this. If you push up, it does not have the log base function, so it would be right under here, and you would have that, and newer calculators would have that fine, and that would be under the math function. But the change of base formula works out just the same too, so that's pretty nice. Alright, thank you for watching.